Hello, I'm Alex, and I'm going to talk about our paper, The Power of Few Qubits and Collisions, Subset Sum Below Grover's Bound. This is a joint work with Alexander May, who is also from Ruhr University Bochum. For the structure of my talk, we first want to talk about the subset sum problem, and then I will show you a brief overview of algorithms solving this problem. After that, we dive in our main contribution, where we construct an algorithm solving the subset sum via collision search. At the end, we want to discuss our results and would like to mention some open questions and further directions. Let us start with the definition of the subset sum problem. For subset sum, we are given n numbers, a1 to an, defined modulo 2 to the n, and a target t, also a number defined modulo 2 to the n. We are asked to find a subset of the AIs that sums up to the target t in z2 to the n. The subset here is represented as a bit string e. We will only consider random instances where the AIs are chosen uniformly at random. And for simplicity, we assume that the size of the subset is equal to n half, which means the bit string e has Hamming weight n half. So why should we care about this problem at all from the cryptographic perspective? That is mostly due to its cryptanalytic applications. There are several problems of cryptographic interest which can be formulated as some vectorial approximation version of the subset sum problem. For example, decoding of random linear binary codes or the short integer solution problem. And so improvements for the subset sum problem often directly relate to more efficient algorithms for the respective problems of cryptographic interest. Let us now have a brief look over a collection of algorithms which solve the subset sum problem. In the table, we can see the exponent of the runtime complexity and the exponent of the memory complexity for each algorithm. First, we have the brute force approach with asymptotic runtime complexity 2 to the n, which needs only some polynomial amount of memory. Then, 1974, Horowitz and Zani improve this with some meet-in-the-middle approach down to 1/2 by using an exponential amount of memory. After that, there are further refinements by distributing the solution in more partial subsets, and later by the use of the representation technique. The complexities do not play an important role for us at this point. If we start now to think about quantum algorithms solving such a problem, it's a common way to first look at the existing classical algorithms. Maybe we can build a quantum version out of the classical algorithm. For example, by replacing some subroutines with some quantum algorithms. And this is exactly what happens in the subset sum case. For every classical algorithm, a quantum counterpart has been constructed. Instead of brute force, we can use Grover, and instead of the classical meet-in-the-middle approach, we can do some 1/3, 2/3 distribution. Or the algorithms gain a speed up by some quantum walk search. If we now take a closer look at these quantum algorithms, we can see that except of Grover's algorithm, every of these quantum algorithms use quantum random access memory. The usage of QRAM is still controversially discussed, and it's not yet clear how much does the realization of QRAM cost us. And it's also unclear how many qubits we need for this. Apart from that, most of these algorithms, which based on the quantum walk search, need an exponential number of qubits. So concerning the development and scalability of today's quantum computers, we want to focus on quantum algorithms which work without QRAM and only with linear many qubits. Sure, there's Grover's algorithm, but perhaps we can do it better. So the question is, can we beat Grover without QRAM by using only linear many qubits? It is known that for the unsorted database search, Grover is optimal. And sure, we can see subset sum as an unsorted database and use Grover to solve it. But subset sum is more than an unsorted database. The subset sum problem has several properties, and maybe we can make usage out of the structure of the problem. So, as we talked before about the common way to construct quantum algorithms out of classical algorithms, we look at some classical algorithm who only needs a linear or maybe a polynomial amount of memory. And we see most of these algorithms heavily rely on collision search. So maybe we can work with some collision search algorithm. And then thinking about quantum algorithms for collision search, we took a closer look at the contribution of Chailloux, Naya-Plasencia and Schrottenlohr from 2017. They constructed a quantum algorithm for the collision search problem, which fulfills all our conditions by using linear many qubits and not working with QRAM. In the further course, we will call this algorithm the CNS-Algorithm. And before diving in this algorithm, let us give a short definition of collision search tailored to our needs. Given two random functions, h1 and h2, mapping from their respective domain to f2 to the n, we are looking for a collision xc, xq, where h1 of xc is equal to h2 of xq. Okay, now the CNS algorithm works as follows. We have the domain S1 on the left with elements xc, and on the right the domain S2 with elements xq. We call xc the classical half because we have to store xc in a classical list during the algorithm. And we call xq the quantum half of the collision. So in the first step, we construct a list L where the elements consists of two entries, xc and the regarding functional value h1 of xc, where the last r bits of this value are fixed to a predetermined value. This is done by some Grover search over the domain S1 to find some xc where the last r bits are equal to a fixed predetermined value. So performing a Grover search gives us one element. So to fill our list, we have to iterate the Grover algorithm again and again and again until we fill our list. And the list size should be at least as big as that we expect to find a collision between a list element and an element xq from S2. So in the second step, we do some amplitude amplification, which is a more general version of the Grover search and consists of a setup and an oracle. In the setup, we start with a superposition over the domain S2 and create a superposition over the elements xq, which also fulfills the condition to the last r bits of the functional value. We assume to do this with some suitable Grover search, without the final measurement at the end. For the oracle, we use a set membership oracle, which states out for every xq if there exists an xc in L where the functional values are equal. So this set membership oracle was first constructed for the CNS algorithm and works without QRAM. But the downside of the oracle is that the evaluation of it takes time linear to the list size. With the setup and the oracle, we execute our amplitude amplification and receive an xq for that a matching xc in L exists. So now we want to make usage of this algorithm for the subset sum problem. So we define two functions, sigma 1 and sigma 2, where sigma 1 computes a corresponding subset modulo 2 to the n, and sigma 2 computes t minus the corresponding subset sum modulo 2 to the n. By the definition of our functions, it's easy to see that every xc and xq, which sums up to the solution E, gives us a collision between our two subset sum functions sigma 1 and sigma 2. For the reverse direction, we have to be more careful. Not every collision, xc and xq, gives us a solution of the subset sum problem. If we add two vectors with 0 and 1 entries, we can get a vector with 2 as an entry. And this kind of vector can't be a solution for the subset sum problem. So we call this property the consistency of the collision. A collision xc and xq is consistent if the sum of xc and xq is a vector of length n with only 0 and 1 entries. And now we have the equivalence. And by this equivalence, we have to it's clear that now we have to find a consistent collision to solve the subset sum problem. We keep this in mind and collect everything we need to adapt the CNS algorithm for the subset sum problem. First, we use sigma I instead of hi. And the second point, we have to add the consistency query to the oracle. And the third point, we have to choose the domains S1 and S2. And this is very important because the choice of S1 and S2 gives us the number of representations of the solution, which is equal to the number of consistent collisions. So every representation is also a consistent collision. Let me give you some examples for S1 and S2. Here S1 contains every bit string which ends with n-half zeros, and S2 contains every string which starts with n-half zeros. Then for a unique solution E, there exists only one representation, and so only one consistent collision. So this is not really a good example for choosing S1 and S2. And now we want to increase the number of consistent collisions. So we choose S1 and S2 equal to the set of n bit strings with Hamming weight n over 4. For every xc where the n-fourth 1 entries are in a position where the solution E has its n-half 1 entries, there exists a suitable counterpart xq. So for a unique solution, we have n-half over n-fourth many representations xc plus xq. This can be further improved with -1 entries. So with this -1 entries, every 0 entry of the unique solution you can represent as a sum of 0 plus 0, -1 plus 1, or 1 plus -1. So there are more representations now by the use of this -1 entries. And yeah, we adapt the CNS algorithm and use the representation technique with -1 entries and achieve the following result. So the adapted CNS algorithm solves a random subset sum instance by using only linear many qubits in expected runtime 2 to the 0.48 n with classical memory 2 to the 0.24 n. And first, it seems to be a success because we go under the Grover bound. But if we need 2 to the 0.24 n classical memory, there exist pure classical algorithms which perform better. So we have to improve the algorithm and find out that we can just do it by replacing the list construction step. Grover is not a good choice to build our list, because for every single new element, we have to run Grover again. Creating a list with many elements, there exists pure classical algorithms working faster. For example, a version of the algorithm of Schroeppel and Shamir, which can be used to solve the whole subset sum, but also to construct a list of elements in the required shape, which means the fixed last r bits. For the algorithm of Schroeppel and Shamir, the domain S1 is represented as a Cartesian product of 4 base lists, so that we can represent every single element of S1 as a sum of 4 elements from the different base lists. The base lists then can be merged, and during every list merging, a condition to the last bits has to be fulfilled to filter out some elements. By doing this, we get a tree structure with our required list L in the root of the tree. With this purely classical approach, we can speed up the list construction, which helps us to optimize the whole algorithm. Now our algorithm needs time 2 to the 0.43 n and needs classical memory 2 to the 0.29n. Similar to the first result, we use -1 entries for our representations. So our domains S1 and S2 contain strings of length n with relatively 1 over 4 plus alpha 1 entries and alpha -1 entries, where alpha is a parameter which has to be optimized. For most classical algorithms, this symmetric distribution is optimal, but in our case, we have on the one hand the pure classical list construction step, and on the other hand the amplitude amplification, a pure quantum step. So why should this symmetric idea be optimal for us? So we make it more flexible and introduce another parameter c. Now, in the first part of the string, we have still the known symmetric distribution over S1 and S2, but in the rear part of the strings, the elements of S1 have only zeros, and the elements of S2 have bit strings with relatively 1/2 entries. This more flexible variant provides us with adjustable domain sizes, but also with less representations. So we have to optimize the different parameters. But besides the whole optimization, we can see if we choose c equal to 0, S1 consists of the 0 vector and S2 of every n-bit vector with Hamming weight n/2. Then our algorithm works similar to the normal Grover search. If we increase then the parameter c, the size of the domain S1, and so the list size increase, which represents the required classical memory. So by the parameter c, we can adjust the memory consumption and we receive the following trade-off. T is now equal to 2 to the n/2 over m to the 0.25 for any classical memory lower or equal 2 to the 0.29n. And we can see it in the diagram here, how our algorithm performs for different amounts of memory. On the x-axis, there's the memory exponent, and on the y-axis, the time exponent. The red line shows the imaginary Grover bound with time exponent n/2. And the black cross shows us the result of the first CNS adaption. And the blue line is our received trade-off. Our trade-off starts at the Grover complexities and achieve a speed up by providing classical memory. In comparison to Grover, we improve for every exponential memory consumption. But now we also have to compare our results to classical trade-offs. And there exist several of them, and in the graph, the dashed line shows a summary of the best classical trade-offs in their respective domain. As we can see for memory exponents greater than 0.2n, the classical trade-offs perform better than our algorithm. And our improvement for solving a subset sum problem is in the range below 0.2n, which is shown by the scripted area. Let me summarize the results of our paper. We built an algorithm solving the subset sum problem faster than Grover while using only linear many qubits and not working with QRAM. We achieve this by adapting the CNS quantum collision search algorithm. Then we improve this by replacing a subroutine and achieve a time memory trade-off starting at the Grover complexities and performs best for classical memory consumption to lower or equal 2 to the 0.2n. And now at the end of my talk, I still want to mention some open questions. There's still the question if we can construct a quantum algorithm which performs faster than Grover without the use of classical memory. And another direction would be to adapt our results to other cryptographic applications and what other resulting complexities we can achieve there. And finally, I hope I could motivate more people to work on quantum algorithms without using QRAM, because this class of algorithms can run on quantum computers in maybe 10 to 15 years. So that's from my side. Thank you very much.